interesting talk. So today we'll also be focusing on how you can build AI-based applications which are completely running offline, because there are multiple use cases, right, which has been occurred these days, where you need privacy, security, and most of the people who work in enterprises, they have very confidential data, and they don't want the data to be shared across the closed source LLM models, right? So this is where having a stack which helps you build your entire pipeline, like from the vector search, the embeddings, and as well as LLMs running locally is very important. So this talk is majorly based on the experiences that we had based on the POC that we developed. So I'll be sharing all the information on what is the tech stack involved, what is the applications we are trying to build. Then we'll also focus on performance trade-off and as well as optimization. So that is going to be the focus of the talk, and we'll be using Qdrant Edge, which helps you to run your vector search engines completely on your on devices. It can be IoT devices, mobile devices, or everything which is completely local. And for the LLM inference, we'll be using Google LiteRT. To someone who has been very close to machine learning, you might have known you have something called as TensorFlow TF Lite. So this is just the rename of the TF Lite, which is LiteRT. So the library that we will be using is LiteRTLM, which is focused on language models. So here is a quick intro about myself. I work as a founding engineer for Kaiwi Labs. The major focus is self-improvement pipelines and devals. And apart from that, I'm part of Google Developer Experts program since 2023. The category is VLLM. And I love contributing to open source. I've been part of Google Summer of Code 2024 at Red Lab. And in 2023, I was part of CM Microscope. All right. So, as I said, we'll be working on an AI application which is completely running offline, which is on your on device. So, what we'll try to do is when we talk about this AI application, it's very simple. It is nothing but your traditional RAG. So, someone who is learning RAG for first time, so RAG stands for Retrieval Augmented Generation. So, basically, you have two parts. So, the first part is your document ingestion, and your second part is your answer generation. So for document processing, basically you have your own data. So this data can be in any format, whether it is PDF, YouTube, CS, not CSV, but you have PDF, YouTube, you have document. Then if your data is in Google Drive, you can also use those things. And once you have your data, you have to chunk your data so that you give the right information and you also don't overflow your context window. So it's better to chunk. There are multiple ways to chunk your data, whether it is semantic chunking, parent-child chunking. So you can choose which approach works for you. And then we also need embedding model, which needs to run locally. Once you have your raw data and as well as embedding model, you use both this information and save it in your vector DB. So once your data is saved inside your vector search engine, you can use search, right? So now what you can do is you have a query. So this is answer generation. Assume you have a UI. In this UI, a user will ask his query. It will be converted into embedding. You're looking into your vector search engine, get the right context. Once you have the right context, if you notice here, you have both query and as well as context, which is going directly to your LLM model. So this LLM will generate the final response. So this is the application we'll try to build. So whatever you see in the red box is your index.py, which is basically data ingestion. And whatever you see outside, it is basically your app, right? It can be running on your Slack chatbot, anything on website, or if you have any local devices, it is running on those things. All right. Now that I have spoken about the application which we'll be trying to build for this particular session, now let's talk about the stack, right? So as I said, everything which we are planning to run has to happen on device. So the major focus will also be what are the relevant models and the relevant technique that we can use so that you have the memory constraints in mind. Because when you're working with on device, memory usage is very important and as well as the performance. So here for embedding model, you have two embedding models which are capable of that. One is Qwen 3 embedding 0.6 billion, and then you have embedding Gemma 300 million. Now, if you look at the benchmark scores, usually you have something called as MTEB leaderboard. So this model usually have all the embedding models. So there are different numbers that you will see. If I just open this multilingual, So if you notice here, you have different categories across which you are benchmarking your scores. So the major focus which I'm using is the re-ranking and retrieval because I need it for RAG-based application. So that's where I've just taken these two numbers. So if you look at Qwen, for re-ranking it is around 61.41, whereas for embedding Gemma it is 63.25. It's not much of the difference. But the same thing, if you look at the retrieval, which is to fetch the right context, you have around 64.67 for Qwen, and for Google embedding Gemma, it is around 62.49. And then you also have different category, which is for English languages. For English, Qwen has around 48.18 on re-rank. Same embedding Gemma has around 47.43. But the retrieval score of Qwen is bit good when it comes to English languages, which is 61.83. So for the demo, we'll be going with Qwen 3 embedding, but you can also pick embedding Gemma based on your use cases. All right. So now that we have spoken about embedding model, now you have your data, you convert that into embedding model. Now you need to save this embedding somewhere, right? So that's where we have Qdrant Edge. So Qdrant Edge, if you have used vector databases, you might have come across the cloud version of it, right? So cloud version is basically your client server architecture. But when it comes to Qdrant Edge, it is basically running on device. So here, the operations that you're performing, whether it is vectorization, payload, quantization, it is similar to what you use in cloud. So the concept here is you have something called as edge shard. So this shard is your storage unit. It's a kind of container unit where you are running your ingestion pipeline and as well as search pipeline. So here, ingestion and query, it is happening on device. As I said, on device can be IoT, mobile devices, or anything which is running locally. Now here I released one more library. So this library is basically the same version of Qdrant Edge, but for ARM v7, which is your Linux architecture. So this is for someone who wants to run Qdrant Edge on Raspberry Pi IoT devices. So this is the GitHub repo, and I'll be sharing all the resources at the end. So I'm just sharing the context. So once you have your embedding model, you are converting your data into embeddings and then saving it in a Qdrant Edge. And lastly, you have your LLM generation, which is once you get the context, you need to generate the final response. So here we'll be using Gemma 4 family series. So in Gemma 4, you have different version. You have Gemma 4 E2B and E4B, which is mainly focused for edge devices. Then you have Gemma 4 31 billion parameter model. This is mainly focused for fine tuning, and as well as if you have good use cases on question and answers or anything which is related to document generation like RFP, then PRD document generation. So for those use cases, this is pretty good. And then you have Gemma 4 26 billion parameter model. This is just the lighter version of 31B, but usually this two is something that you can probably prefer for use cases. For on device, in our demo, we'll be using E2B. So all right, so now that I've spoken about, okay, we'll be using Gemma 4, but how are we running it, right? So in order to inference our Gemma 4 locally, we will be using LiteRT. And as I said, to those who have been into ML, TF Lite was one of our favorite library during those days. So TF Lite was renamed into LiteRT. Now the concept is similar. You have your own model, you're training your own model, and once you save it in a TF Lite format, which is now LiteRT. If you're using LLMs, it is LiteRT-LM. So that is your extension which you're trying to create. And as I said, since we'll be also working with LLMs, you can deploy generative AI models. So this is one of the feature. And last but not the least, which is one of the major feature of Google AI Edge, which is LiteRT, it provides different hardware providers. So these different hardware providers are you have CPU, GPU, NPU, and TPU. So for NPU, you have Qualcomm and as well as Intel. So for TPU, obviously you have Google itself. And there are other features as well, like if you want to build mobile applications like Android, iOS, or web-based applications, LiteRT is cross-platform, so you can prefer that as well. And as I said, you have different hardware accelerators like GPU, NPU, CPU, and as well as TPU. And last but not the least, you also have this different framework support. If you are building your model through PyTorch, you can also convert that into LiteRT. Same goes for TensorFlow or JAX. All right. So before I can go with the performance part, I just wanted to see if there are any questions, or we can proceed. Perfect. So what we'll do is we'll proceed. What we discussed so far is the application, which is RAG. Then we discussed about the tech stack, where we are using embedding models like Qwen 0.6b, and then we have Qdrant Edge, which is our vector search engine, and then Google LiteRT for LLM inference. Now, once we know the tech stack, obviously there are two things we have to keep in mind. First, the performance. Second, the optimization. So here I'll be talking about performance. So when we are working with search engines, right, you need to get right context. So these days you might have heard about harness engineering. So harness engineering, there are multiple things. You have observability, you have your context engineering, memory, evals, and many other things. So model is just a smaller part of it. So the better harness part you have, which fetch you the right context, it is very important. So one part of harness engineering also includes your retriever engines. So retriever is basically your search pipelines. So here we'll be using hybrid search whenever we want to retrieve our relevant information. So here is an example. Assume your query is related to neural network. You have two different kind of vectors. One is dense vectors and one more is sparse vectors. So sparse vectors or keyword search. So basically, few people call it as keyword search, few people call it as lexical search. So here we are using sparse vectors. So what typically happens is, if you're searching for neural network, you will get those context which only has neural network. So if there is any information or data which is related to deep learning and AI, it will not be included. So what keyword search does is, it will just do mapping. What are the matching keywords, right? Then you have vector search. So vector search uses dense vectors. So here, if you notice, if you're searching for neural network, you will find the information about neural network. You will also find information which is related to deep learning, AI, and machine learning. So vector search is based on meaning, right? Semantic meaning. So what hybrid search does is, once you have user query, you have dense embeddings, which is your vector search. You have sparse embeddings, which is your keyword or lexical search. Once you have these two vectors, you're just using the hybrid search, where you're creating the fusion, you're combining them. Now, how do we combine this? You have a search, the fusion technique, which is reciprocal rank fusion. So there are two kind of fusion which happens. One is reciprocal rank, and one more is you have DBSF. So in reciprocal rank, we only focus on rank. For example, if you are retrieving 5 context, assume you are getting 5 context from dense, you are getting 5 context from sparse. Based on the rank which was retrieved first, you are creating the rank positions. Then you have DBSF, which is mainly focused on retrieval scores. So every single context you get in vector DB will have a semantic scores. So based on the scores, you are creating the fusion. So once you have the fusion, you have the context which you are giving it to the LLM. So this is the part we are focusing on. So whatever this context you are giving it to the LLM, we need better context. So this three, if you notice, this three is where your hybrid search will happen, which will combine your dense embeddings, sparse embeddings, user fusion, and give you the context. All right. So once we are aware of the search technique that we'll be using for better performance, let's also talk about trade-off and optimization for both LLM and as well as vector search engine. The first thing is, you have quantization technique. There are 4 different quantization support which is provided by Qdrant Edge. One, you have turbo quant. Then you have scalar quantization, binary quantization, and product quantization. Again, this is a complete different topic, where you have different ways for which particular application which quantization works. But these days many people prefer turbo quant, because it is the research which was done by Google team itself. You can just search for turbo quant. The research was by Google brain team. The major focus is on the rotating embeddings and how well you can create the compression for the vectors that you're generating, so that you utilize lesser memory usage. So that's where the quantization is important. And in the demo, we'll be using turbo quant. And next, LiteRT. So since we are using Gemma for LLM, there might be times you might need the quantized version of it. If not, you want to fine tune it. There was one question on fine tuning, right? So first you need to ask the question whether you need to optimize the model or not. If you don't want to optimize, you can directly use the LiteRT LM model. Now, if you want to optimize it, there are again 2 ways. One, you can use post-training float 16 quantization. A few people also use QAT, which is quantization aware training. So this thing is something which was already shared by the previous speaker. But when it comes to LiteRT, there are some models which are not directly supported with the kernel. So you can just check which techniques works with LiteRT kernel, and you can use the post training accordingly. And if you need more effort, so here what you need to do is you need to train your model again. So for training, typically you create your data sets. So once you have your data set, you just check whether you need further training or not. And this decision tree is something which is very useful when you want to decide whether you want to train it more, or you want to use quantization, or you can stop it, right? So this is the decision tree, and I'll also share the resources at the end. All right, now that we are focused on trade-off, performance, and as well as the tech stack, I'll quickly show you the demo, and as well as you can get the source code as well. So this is the flow which we'll be trying to work on. You have the source documents, it's a PDF, and once you have the PDF, we are using Edge parse so that we can extract the raw information from PDF. So what Edge parse does is it will convert our data into Markdown. So Markdown is pretty structured, which helps us to chunk our data as well. And then whatever data you have, you're using Qwen3 embeddings so that you get the embeddings of it. And once you have the embeddings, we are saving it in our vector search engine. So this is the part. So if you notice the cursor, this part is your document ingestion, which is happening in index.py. Once your data is saved, now you have a UI on Streamlit where user will ask a question. You're performing search from your vector search engine. This is giving you the context. Now, as per our previous diagram, I told you for LLM, you are getting two inputs. One is your context, and one more is the question. Once you have both these two things, you are giving it to the LLM, which will generate the final results. So this is the GitHub repo where you have the source code, and I will break down step by step. So this is the GitHub repo for you to refer on whatever we'll be doing today. All right. So first off, as I said, everything whatever we are trying to do will run offline. When I say offline, it is without the internet. But now, if I just disable this, I'll probably end the meet. So I'll not disable it, but you can run it offline as well. So before you can run offline, the first thing is you need to have your models downloaded. So if you notice here on my left hand side, I have Qwen 4, I have Qwen 3 embed. So I need to download the model files. So where am I downloading the models files from? I'm downloading it from Hugging Face. So either you can download it manually. If you don't want to download manually, if you want to write a code which automatically gets you the files. So this is the thing which is happening. So first function is related to embedding model. I'm downloading Qwen 3 model, and this is the repo ID. So if I just copy this, and if I come here, so this is the model which we are using, and what we need to do is we need all these files. So whatever these files are there, right? We need these files which is in our local system. So we just have to download all these things. So one thing is you can directly download it from here. If you're not able to do it, you have this code. So this code will help you to download it. So you have the repository ID, and next you have models Qwen3 embed. So this is the local directory, which is nothing but this models. So whatever model you have, you download the files, you save it in this particular local directory. So same thing is happening with Gemma 4 as well, which is the LiteRT. So if you notice here, the extension is LiteRT, and we are using Gemma for E2B. Now there might be few questions as well, right? Like why are we using LiteRT over Olama? Because Olama also helps you in running your models locally. So there were few discussions that we had on Reddit. So I actually shared the context on how I build this. So if you see, we are using the same tech stack. You have Edge parse, which we are using. Then you have Qwen 3 embeddings, and then Gemma 4, we are using it from LiteRT. And then we had one more conversation on the latency. So if you see the results here, LiteRT LM Gemma 4E2B came out around 609 milliseconds. This is pretty fast compared to Olama, which was running around 743 millisecond, and QAT, which is quantization away training, it is around 837. So the latency of using LiteRT was much better compared to these things, but there were few answer relation quality where LiteRT passed around 4 to 5, but Olama passed all 5 checks. But here for LiteRT, you can improve the prompts to get the better results as well, but which I'll talk about in the demo. All right. So as I said, we'll be using LiteRT, which is the extension to use your LiteRT model. So you just have to download this particular model files and save it inside this folder. So inside Gemma 4, if you notice, I have only one file, which is LiteRT. This is what you need. All right. So once you have these two things downloaded, which is your embedding model and as well as Gemma LiteRT, that's it. You have everything downloaded. Now you can just turn off your internet and run these two scripts. So the first script is index.py. So what is happening in index.py? You have your PDF, you load it, you convert that into chunks. Then once you convert into chunks, use embedding model and save it in a Qdrant Edge. So that is the major focus. So the model that we are using is Qwen3 embed from our local directory. If you see, this is the local directory, and you have a PDF. So PDF is inside the data folder. So this is related to finance. It's related to tax of Indian system. So you have a budget 2026. So that is the PDF I'm using. Now what is happening is you're creating a folder where your data is indexed and saved. So for example, here you have shard path, you have DB. So once your data is saved in a vector search engine, it has to be have a storage unit. So that's where you have this shard. And I also told you in my slides, this is basically your edge shard. So now we start with the document ingestion. So in document ingestion, if you look at, if I scroll below, so first thing is document ingestion. And once you have document ingestion, you're running this index function. So let me call this index function. Okay, so here we are in the index function. So let's go line by line. So the first line is you have markdown. Whatever you are trying to do is edge parse dot convert. Now in this convert, you're passing your path of the PDF. So what will happen is whatever information you have in your PDF, that will be converted into markdown format. And this is directly the library. And once you have the markdown format, you're applying chunk. So chunking is based on the tokens that you're defining. So it's very simple chunking process. So once these two things are done, the next thing is you need to convert into embedding model. So here, if you notice, you have self.model, then encode document. So this self model is from sentence transformers. So if I scroll above, where is self model? So if you notice, you have self.model, sentence transformer, and the model name. So this model name is basically your Qwen3 0.6b embedding model. So this self.model has a function called encode documents. So that is what you're trying to use. Where is that error? You have self.model, then you have encode document. So this function will convert your raw document into embeddings. So once you have into embeddings, the next step is you need to save your data inside a vector DB. So before you save your data into Qdrant Edge, you need to configure it. So we have already configured it earlier. So if you notice here, you have configuration where you have edge config, then you have vector. So here is something very important. Whenever you are using vector databases, so let's suppose you're using any vector search engine. So the first step is you create configuration. So when you create configuration, you define your vectors. So usually there will be dense and sparse. So if you're using dense plus sparse, it's obvious you're using hybrid search. There are few people who will just use dense. They don't want to use hybrid search. So you will have dense embeddings. So for dense, typically you will have dimension. Dimension because dense embeddings are fixed. For example, Qwen models are 1024. Just like that, there are different models which will have different dimension. It can be 386, 756, then you have 512, 1026. So embedding models for dense vectors is fixed. So you have to define dimension. And apart from dimension, you should also define your distance. So distance is basically your cosine. If not, few people also use dot operation, but it's better to go with cosine, which is preferred. So after you create configuration, the second step, what you need to do is you need to create point. This is focused on Qdrant, but the process is same for the other vector DB as well. Here, what you're supposed to do is, first thing is you have ID. ID is unique. Then you have vector. So vector is nothing but whatever raw data you have, you're converting your raw data into embeddings, and this embeddings is saved inside your vector parameter. So once you have vectorization, the last thing is you have payload. So why is payload required, right? Let me tell you that as well. Assume I have 100 PDFs, and now I have a user question. Let's suppose you have something like XYZ. Now, whenever you ask this question, you need to look into this 100 PDFs and generate the response. So when you are generating the answer, you also need to tell from which PDF this was generated and from which page number. So again, I'll repeat, you have 100 PDFs, you ask a question, which is anything related to this 100 PDFs. Now, once you get the answer, along with answer, you should also need to generate citation, which will tell from which PDF you generated the response and from which page number you generated it. So you need these two citations. So what we typically do is we save that in our payload. So whatever metadata you have, you're saving that in your payload. So these things are very important. Once you create configuration, second you create the point where you're adding all these three parameters. One is ID, vector, and as well as payload. Once you have this information, you just upload or upsert. So this will create your shard where your data is already saved. So you just have to do these three things. Once you do these three things, the first step is done. So the first step is basically your index is completed. So here we created the space. So if you notice, you have edge config. We are only using dense vectors. I'll also show you how it differs in hybrid search. So edge vector params. So this vector params is your dense. You define your size, which is 1024, and your distance is cosine, similar to what you have mentioned here. Dimension and distance. And once this is done, you are just checking if the shard is already present or not. If it is present, you're just loading it. If it is not present, you're creating a new shard. It is simple. So if you see here, if shard exists, just load it, the existing one. If it is not existing, just create a new one. Solid. So this is the first step. And once you have your configuration, the next thing is you need to update it. So for update, we use something called as point. So if you notice, this is your ID. If I hover on this, there are three things. Can you see it? One is ID, second is vector, and third is payload. So if I scroll below, this is your ID. Now this is your vector, and whatever this metadata is there. So this metadata is basically your payload. So always remember your metadata is a dictionary. And once you have your data saved, the only thing is you're running optimize. And once you run optimize, your data is saved in your shard. So we completed till this part, which is indexing. So now once you index your data, it will take around few minutes to index it. Now once this is done, we need to test whether it is working or not, right? So if I scroll below, uh, we first created a report, and then you created your ingestion pipeline where you're passing your document files. So indexing is done. This part we have completed. This part is completed. And once you complete this, it will create a new folder. As you can see, you have a new folder here, which is DB. So inside this DB, you have your shard storage unit files. Now, once your data is saved, the next thing is I want to test whether it is working or not. So I simply ask a simple user query like, what is the budget allocated for Biopharma Shakti project? So this user query is from the PDF. Then you need to get the context. For that, you are just using ingestion dot inference. So now let's just test this function. So inside this inference, what you're trying to do, you have a user query, you're converting that into embeddings. So once you convert into embeddings, you're using search. So results equals to shard dot query. Here you're passing your user information and then limit. So for the given information, how much chunk do you want, right? So that is your limit. I just need two chunks. So once you get this result, you're only extracting the payload, which is the text. So once you have the context, just return the context. It's very simple. Just convert your user information into embeddings using your self model encode. This is your Gemma. And once you convert into embeddings, next thing is search. So for search, you define your embeddings and as well as limit. Limit is basically how many chunks do you need, whether you need 2, 3, or 4. All right. So once this is done, you get the final result. So if I show you the terminal, let me run it again. So what I will do is I will delete DB and I will run it freshly. So let me delete this. And now I'll just run Python index.py. So first what it will do is it will download the model files. Once it loaded the weights, it will tell you how much chunks do you have, right? So for the PDF that we are using, it should have around 80 to 90 chunks or 60 chunks, I'm not sure. So it will show you the number of chunks it is indexing, and then it will create a folder. So it has created a folder. Now it will just tell how much chunks it was utilized, and it will also give you the results for our inference. So it should take around few seconds. I didn't got disconnected, right? Usually there will be some lag. Was there any lag? Hello? Okay, I'm audible, right?
Yeah.
Okay. So now if you can see here, it ran the particular loading models. It indexed around 93 chunks. So this 93 chunks is basically whatever PDF you have, you convert into Markdown, and then you have chunks. So you have around 93 chunks. So next thing what it did is it generated the relevant context. So if you notice here, whatever this information is there, this information is for the question you have asked. So if you see here, you have biopharma project, and all this context is related to that. And then it will also give you the report on what was the latency for loading the model, what was the latency for chunking, what was the latency for ingestion. So all this information is saved here. And then if you notice, you have the query. So search took around 3.5 seconds, and it will also tell you how much RAM it utilized, because this information is important when you're working with IoT devices. All right. So now that we know our index.py is working, the next and the final part is your app.py. So in app.py, what we are trying to do, we ask a user question, get the context from Qdrant Edge. So how do we get the context? Same code. First you convert into embedding. Once you convert into embedding, get the results. Now once you get the result, you give to the LLM. So for LLM, we will be using import LiteRT LM. This is mainly for generative AI models to run on Google LiteRT. So the extension should be LiteRT LM, which is .LiteRT LM. All right. Now remaining things are same. You're using Qdrant Edge for querying to get the search, and you're using sentence transformers so that if I ask any user query, I need to convert that into embeddings first. And I've showcased this in my diagram as well. So if you see here, once you ask a user query, you convert into embeddings, then look into VectorDB, and then you get the context. So these two things are same as per what you have used earlier. The only new thing is LiteRT. So we define our path. So the model path is inside models Qwen3 embed. This is our embedding model. Then shard, our vector search engine, is saved inside DB. Then you have Gemma for LiteRT, which is again my local directory. Inside my local directory, have Gemma folder. Then you have LiteRT LM. So everything is local. And the major new thing what you will notice is we are creating this engine. So if you notice, you have Light RTLM, you're creating an engine. So inside this engine, we pass our Gemma model. So this Gemma model is running on GPU backend since I'm using Mac. So this engine is something that you are creating first. Once you create the engine, just create a prompt template and pass that prompt to your run function. That's the only three step. Create the engine, create your prompt template, and give it to your runner. All right. So if I scroll below, you have the retrieve context. So if you look at the syntax, it's the same thing what I mentioned here. First thing is you have query vector. You have query vector, which is converting your user query into embeddings. Once you convert into embeddings, you're running query. You pass that into query. Then limit is 2. I only need to get 2 chunks which are relevant. Then payload is true so that you can get your payload information as well. That's it. Once you have your payload information, just return the context. And now for engine, as I said, there are three things. First, you define the engine, create your prompt template, and run it. So this is the prompt template. I'm defining my system prompt. You are an Indian budget assistant. Answer the user using the context provided. If the context is missing, you just say I don't know, so it doesn't hallucinate. And answer in 1 or 2 short sentences, and do not elaborate unless user told you to do it, because I need faster responses. So once you define your prompt template, it's the same thing. You're getting your messages. Once you create your message, you need to use your conversation. So inside this conversation, you're just sending your message. So this is the running part. Once you run this, I'm streaming it. So what happens in streaming? It's similar to ChatGPT and Gemini. If you ask a question, you're not waiting until you get the final response. You have one token at a time. So this is what is happening here. I want to see one token at a time when you're generating the results. I will show you this in the UI, this part. I will show you this in the Streamlit UI. And once you do this, you have your final answer generation. I'm testing across 5 user queries. So if you see, you have a question on Biopharma Shakti project, which I asked earlier. This is from the data. This is from the PDF. This question is also from the PDF. Now, if you notice the third question, it is a very tricky question, which is not from the PDF. This is not from the PDF. And then you have one more question, which is from the PDF. So now what I'm trying to do, I have this 4 user queries. I will run this across my Google LiteRT. So this is the Gemma inference. So if you notice, we are just retrieving the context. Once you retrieve the context, you are streaming it. So what happens in streaming? It will generate one token at a time. So let me open my terminal, and here I will just run python app.py. So what it will do is, first it will load your model weights because we are using an embedding model. And once it loads it, the next thing what it will do is it will ask one question at a time. So what is the budget allotted for Biopharma Shakti project? The response was pretty quick. It is around 10,000 crores in Indian rupee. And you have the second question, you got the context. So now if you look at the third question, the context mentions a section for indirect taxes, but it is not specific. As I said, it was a wrong question, which is not from the PDF, and it was able to generate the results. And last one was from the PDF, and it give the right results, and it will tell you how much latency it took. So if you notice, LiteRT engine was roughly 1 second, which is pretty good in generating the results. And you can check the answer generation part. So answer generation 1.89, this is the LiteRT inference. Then answer generation, it took around 2 seconds. This one around 1.83. If you notice the context is also less than 1 second. So this is the Qdrant Edge part, which is running on edge device. So the latency is pretty less, and it took 13 seconds to generate 4 results, right? Now let me show you the streaming results on UI. My UI is already running. So this is the Streamlit UI, which is running on localhost. Even Streamlit is running offline. So if you turn off internet, you should still be able to answer the question. So I will just copy this question. What is the biopharma? And first time, only the first user query will take some time since it is loading the model. So once you load the model, if you notice this UI part, here I'm using cached resources. So once you have your data in cached resources, the next question becomes very faster. So which I'll show you in a bit as well. So let me copy the second question. So you already have the response. Now I'll ask the second question. You will see it will generate one token at a time. So this is one token at a time, which is streaming. So if you don't stream your data, if you directly print the response, it will wait at the end and then generate you the results. So now this is pretty fast. So let me copy one more prompt. And yes, as I said, everything is local. You're not using any APIs, you're not using any cloud. Everything is happening in your local system. So this is what I wanted to showcase. First index, second app.py. And a small change, since I also told you about hybrid search, let me show you the code for that. So inside the same project files, you have hybrid search performance. There you will see index.py. So there are just few changes that you need to notice. Earlier, when you created configuration, you only created for vector, which is dense embeddings. Now what you're trying to do, you're also creating for sparse vector, which is basically your sparse. So this is the only change first. And then when you create your points, you should also define your sparse vectors. And once you create this sparse, when you're using search, you need to use something called as RRF. So if I scroll below, so now if you look at the inference, you have your dense embeddings, you have your sparse embeddings. This is as per the diagram. So if I show you the diagram, you have the user query, you're creating your dense embeddings and sparse embeddings. So this is your dense, this is your sparse, and then you need to combine it. When you combine, you have to use something called as fusion. So this fusion is basically your RRF, so reciprocal rank fusion, and you can define any point. So I'm just using the default. Once this is done, the other parameters are same. Limit is basically top two chunks, and payload is true, so that you can get the text information. Once you pass this result, you're just generating the results. That's the only change. First, define your configuration where you have sparse. Then if you scroll down, when you're creating points for vectors, there are two. One is dense and one more is sparse. Your payload is same, your ID is same, and that's it. These are the things you are doing in your indexing. Then for inference, you are creating two different search for dense and as well as sparse embeddings, and then just use fusion. So this code is also available, you can go check it out. The inference file is same. So if you open the inference file, you have the same model, you have the same prompt, and you have the same engine. So here nothing is changed. All right. If you have any questions, we can take the questions. And for future videos, a bit of self promotion. I've already released the same video on my YouTube channel as well. But if someone is interested in learning about evals and agentic RAG and everything around agents, you can just check out this channel. And this is the QR code for the YouTube URL. And you can also check out the socials. Yeah. Do you have any questions?
So I can stop